Welcome to Talk Tensors, the deep dive where we take a fascinating machine learning research paper and really try to pull out the key insights for you.
Glad to be here.
Today we're diving into, a pretty big challenge in AI. How do we actually look inside the black box of these really complex neural networks and figure out how they tick?
Exactly. We see these incredibly powerful models popping up all the time, don't we?
Yeah.
But understanding why they do what they do, that can be, well, murky.
Yeah, definitely murky.
So our goal today is to shed some light on a new academic paper that's making, I think, some really interesting progress on this interpretability front.
Okay, great. And the paper we're looking at is titled Explainable Bayesian Deep Learning through Input-Skip Latent Binary Bayesian Neural Networks. It's by Highheim and colleagues, a 2025 preprint. Sounds like a mouthful.
It does sound a bit dense, yeah. But the core concepts, they're actually quite elegant. Yeah. And they could really make a difference in how we approach AI understanding.
So for our listener, the learner, what's our mission with this deep dive?
Right. For you, the learner, we want to break this paper down.
Yeah.
We want to highlight what's genuinely important, understand how it tackles that tricky balance, the amazing accuracy of modern networks versus their, let's face it, often frustrating lack of transparency.
And we'll do it thoroughly, but hopefully without drowning in the super technical stuff.
That's the plan. Keep it accessible, but insightful.
Okay, so what's the roadmap? We'll start with a general summary. What's the paper about? Why should we care? Then we'll maybe take a little step back, look at the history, the context that led up to this research.
Give it some background, yeah.
And finally, we'll peek into the future a bit, discuss some novel notions, new ideas this paper might spark. Sound good?
Sounds great. Let's get started.
Okay, so jumping right in. What's the main problem this Highheim paper is trying to crack?
Well, fundamentally, it's tackling two big headaches with a lot of current artificial neural networks, or ANNs. First, interpretability, like we said, just understanding why a network gives a certain prediction. How do the inputs contribute?
Right.
And second, how these networks handle uncertainty. Are they sure about their prediction or just guessing?
You see these super complex networks, like, say, GPT-4, amazing outputs, right? But it is, as the paper notes, basically a black box.
It really is. We don't precisely know why it generates that specific sentence or makes that connection. And that makes trust difficult, especially when it sounds very confident but might be off.
Yeah, and figuring out which specific input features, the covariates, are actually driving the decision. That's tough too.
Absolutely. Imagine using AI for, say, medical diagnosis. It flags something, but you can't easily tell which symptom or test result was the key trigger. That's a real barrier.
Okay, so the paper mentions Bayesian Neural Networks, BNNs. Are they part of the solution?
They're a step in the right direction, particularly for the uncertainty part. BNNs treat the network's weights, its internal parameters, not as single fixed numbers, but as probability distributions, ranges of possibilities.
So instead of one answer, it gives you a range and how confident it is.
Exactly. Think of it like a weather forecast saying 80% chance of rain instead of just it will rain. It gives you more nuance, what they call credibility intervals. It helps manage expectations about the prediction.
That definitely sounds useful for knowing how much to trust the output. But the paper implies BNNs still have problems with being easy to understand.
That's the catch. Yes, they handle uncertainty better, but they can still be incredibly complex architecturally. Lots of layers, lots of connections, nonlinear stuff going on.
Still a bit of a black box, just a probabilistic one.
Pretty much. Getting a clear picture of the overall logic or why one specific input led to one specific output can still be really challenging. Global and local interpretability remain tricky.
Right. Which brings us to latent binary Bayesian neural networks. LBBNNs, how do they try to simplify things?
Okay, so LBBNNs have this clever trick. They learn to simplify themselves. The core idea is to attach a sort of trainable on-off switch, an indicator variable to every single connection in the network.
A light switch for each connection.
Kind of, yeah. The network learns during training which switches are actually important and which ones are redundant off. By finding and effectively removing those off connections, the model becomes sparse, much leaner.
So it's like the network does its own Marie Kondo-style decluttering, getting rid of connections that don't spark joy. Or predictive power.
Exactly. A bit of internal spring cleaning. And the paper highlights that this approach, considering model uncertainty, should this connection even exist, on top of parameter uncertainty, what value should it have, leads to better calibrated predictions.
Better calibrated. meaning their stated confidence matches their actual accuracy more closely.
Precisely. They're more honest about how sure they are.
Okay, that feels like a solid step forward for reliable probabilistic models. But even these LBBNNs have a limitation, according to this paper.
Yes, even when you have a nice sparse LBBNN, the standard way forces all the input data, all those covariates, through every single hidden layer and nonlinear activation function that remains.
Why is that a problem?
Well, the authors argue it can be inefficient and obscure simple relationships. What if, for a particular input, the relationship with the output is actually quite straightforward, maybe just linear?
Ah, I see. Forcing it through complex hoops might just muddy the waters.
Exactly. It makes it harder to see that simple connection and complicates interpretation unnecessarily.
Okay, so this is where the big idea comes in. The Input-Skip LBBNN, or ISLab. What's the magic here?
The core innovation of ISLab is allowing those input features, the covariates, to essentially skip layers. They can connect directly to any later layer in the network, or even be left out entirely if the model learns they aren't useful for a particular task.
Like adding an ingredient later in a recipe, it doesn't have to go through all the initial mixing steps.
That's a great analogy. Some ingredients only need to be stirred in at the end. ISLab lets the model learn the most efficient path for each input. If the underlying relationship is linear, an input could learn to bypass all the complex hidden layers and connect more directly.
That feels really elegant. So the network architecture isn't rigidly fixed from the start.
Exactly. It learns its own best structure for the problem. This avoids having to guess the perfect architecture beforehand or doing that really computationally heavy neural architecture search where you try tons of options.
Makes sense.
And crucially, ISLab comes with interpretability methods baked right in. Ways to understand the model globally and locally, and these methods have theoretical backing, unlike some external tools like AKA or SAGE you apply afterwards.
And did they see big results in terms of network simplification?
Oh, absolutely. The numbers they report are pretty dramatic. They talk about reducing the number of active weights, the network density, by over 99% for smaller networks.
Wow, 99%.
Yeah, and even more, over 99.9% for larger ones. And crucially, they did this while keeping high accuracy and good uncertainty measurement. They mentioned getting 97% accuracy on the MNES dataset.
The handwritten digits one.
That's the one, with only about 935 weights active. They suggest this hits a new frontier in terms of efficiency for these kinds of models.
That is seriously sparse. So quick recap of the key innovations here.
Okay, two main things. One, putting that input-skip mechanism into the LBBNN framework. This leads to way simpler, more efficient networks and clearer views of input contribution.
Got it. And two.
Two, a novel set of methods that leverage this structure to give us enhanced global and local understanding of the trained network. Basically, better tools to peek inside that black box.
Okay, fantastic summary. Now let's rewind a bit. How did we get here? What's the history leading up to ISLab?
Right, context is key. It helps to trace the path. We started with the basic idea of artificial neural networks, and a really foundational concept is the universal approximation theorem.
Ah, yes, the idea that ANNs can learn pretty much anything.
Essentially, yes. Given enough data in neurons, they can approximate any continuous function. That's why huge models like GPT-4 can tackle such complex tasks. But that sheer power, that massive number of connections, it often leads to the interpretability problem we talked about.
Right.
More power, less clarity.
Makes sense. More going on under the hood, harder to track. And then there was the uncertainty issue with standard ANNs.
Exactly. They typically just give you one answer, take it or leave it, no sense of confidence. This is what spurred the development of Bayesian Neural Networks, BNNs. The paper points to Radford Neal's work, I think back in '92, as being really seminal here.
And the core BNN idea, again,
was treating the weights as probability distributions, not fixed numbers. This lets you get those credibility intervals for predictions, a quantitative measure of the model's certainty.
Okay, so BNNs tackled uncertainty, but still often complex and hard to interpret.
Precisely. The structure could still be vast, which led to the next step. Latent binary Bayesian neural networks, LBBNNs. The paper credits work by Hubin and Stork in 2019 and Bai et al. In 2020.
And their big contribution was the on-off switches.
That's right, those trainable indicator variables for each connection. This allowed the network to learn a sparse structure automatically, turning off connections it didn't need. They used something called the median probability model, MPM, to help decide which connections to prune.
Pruning the weak links.
Exactly. And the paper also nods to more recent work, Scarrett-Lund et al. In 2024, showing empirically that this LBBNN approach really does improve prediction calibration.
So LBBNNs made networks sparser, more calibrated, but still had that issue of forcing all inputs through all remaining layers.
That was the final piece of the puzzle motivating ISLab. Why force an input through multiple complex transformations if its relationship to the output is actually quite simple? It's inefficient and it hurts interpretability.
And how does ISLab compare to other network design tricks? Like, I've heard of dense nets or residual connections.
Good question. The authors do discuss connections to other techniques. They mention things like concatenation used in CNNs like dense nets or UNets, and also in some MLPs where information from earlier layers is passed forward.
So similar ideas about connecting layers.
Similar in spirit, but the authors stress that combining this input skipping specifically with the Bayesian structure learning of LBBNNs is the novel contribution here. ISLab is different. They also contract it with residual connections. ResNets help information flow, for sure, but they don't fundamentally change the number of potential parameters in the same way Input-Skip does.
Gotcha. And to understand these ISLab models better, they introduce this idea of active paths.
Yes, active paths are really key for interpretation. Imagine following the connections from a specific input feature all the way to the output node. An active path is a sequence of on-connections weights that the model decided to keep linking that input to the output. We ignore paths that only involve bias terms.
So it's like tracing the important routes through the network.
Exactly. Focusing on these active paths gives you a much sparser, more direct picture of how the network is actually using the inputs to arrive at its decision. It highlights the connections that truly matter for the prediction.
Okay, history covered. Now for the really cutting-edge stuff, the novel notions. What new analytical tools or concepts does this ISLab research enable?
This is where it gets exciting for future work. Because inputs can now bypass layers, the paper introduces new ways to measure how and where they contribute. They define metrics like contribution depth, max depth, and average depth.
Depth, like how many layers an input effectively passes through?
Sort of. Contribution depth is the length of the active path from an input at a certain layer to the output. Max depth is just the longest active path anywhere in the network. And average depth gives you a sense, across all inputs, of how many steps they typically take to influence the output.
So a lower average depth might mean inputs generally have a more direct impact, less complex processing.
Exactly. These metrics provide quantitative insights into the structural complexity the model learned. And when you combine this with visualizing the active paths in the median probability model, remember, that's the final sparse model, you get a much clearer global picture. Figure 7 in the paper apparently shows this well for a simple linear problem, highlighting just the direct input-output connections.
Very cool. What about understanding specific predictions? Local explainability.
That's another key area. ISLab offers new tools here too, leveraging those active paths and the common use of piecewise linear activation functions like ReLU.
ReLU, the one that's 0 for negative inputs and linear for positive.
That's the one. They present a result, proposition 1, which is quite powerful. It basically shows that for any specific input data point, a ReLU network using ISLab behaves locally like a generalized linear model, a GLM.
A GLM, like logistic regression or standard linear regression.
Exactly. Models where you have interpretable coefficients, or slopes. It means that if you make a tiny change to one input feature, the change in the network's output is approximately linear, locally. And the slope of that linear relationship tells you the contribution of that input to that specific prediction.
Wow, okay, so you can directly quantify how much each input is pushing a specific prediction up or down.
Pretty much, yes. And a huge advantage is that this explanation comes directly from the trained ISLab model itself. You don't need separate post hoc approximation methods like LIME, which essentially train another simple model just to explain the complex one.
So the explanation is intrinsic to the model.
Right. And even better, because it's all within the Bayesian LBBNN framework, they can estimate the uncertainty around these contributions. So you get credibility intervals for your explanations. You know how confident the model is about the importance it assigns to each feature locally.
That adds another layer of trustworthiness. And they mentioned another way to get these local explanations using gradients.
Yes. Corollary 2 follows from proposition 1. It states that for these piecewise linear activation functions, you can get those same local explanation slopes very efficiently just by calculating the gradient of the network's output with respect to the input features, evaluated at that specific data point.
Just standard backpropagation?
Essentially, yes.
Yeah.
Computing gradients is standard practice. While using gradients for explanations isn't brand new, the paper provides the strong theoretical link via Proposition 1 within their ISLab context, showing why it works and corresponds to those interpretable local linear approximations. Plus, it's computationally fast.
Makes sense. The paper backed this up with experiments, right? Any key takeaways there?
Oh yeah, a pretty thorough experimental section. They tested ISLab against several relevant Bayes' versions without input-skip, non-Bayesian methods, etc., on both synthetic data where they knew the true relationship and several real-world data sets.
And the results?
Consistently strong. ISLab models generally achieved high accuracy, but with drastically fewer active weights, like that MNIST example we mentioned.
So efficient and accurate.
Right. They also showed the models adapted their complexity nicely. On simple linear data, ISLab learned basically linear models. On complex nonlinear data, it learned more complex structures, using the hidden layers and skips appropriately.
Smart adaptation.
They often found better calibration compared to frequentist approaches, too. And the visualizations they included of the learned network structures, the active paths, really seemed to provide interpretable global insights. Plus, they demonstrated generating those local explanations with uncertainty estimates, showing how individual features influence predictions for specific examples.
Sounds very comprehensive. Did they mention any challenges or future directions, like how you set up these ISLab models?
They did briefly touch on initialization and optimization. How you initially set the probabilities for including connections can matter, kind of like backward or forward selection in classical statistics. They suggested future work could explore smarter ways to initialize these probabilities, maybe adaptively during training, and also develop optimization algorithms specifically tuned for the unique landscape of these Input-Skip LBBNNs. There's definitely room for refinement there.
Okay, great. So let's wrap this up. What's the main message we should take away from this deep dive into the Input-Skip LBBNN paper?
I think the key takeaway is that this ISLab method looks like a really significant step towards creating deep learning models that are not just powerful predictors, but also much more explainable and efficient. It does this by letting the model learn its own best structure and giving us built-in tools to understand why it makes the predictions it does.
Both globally and locally.
Exactly. Without sacrificing that predictive accuracy, which is crucial.
And for you, our listener, the learner, what's the real value here?
For you, I think ISLab offers a potential way to move beyond just knowing what a neural network predicts to understanding why. By pinpointing the important inputs and how complex their relationship with the output actually is, it starts to demystify the AI's reasoning. That builds trust and lets you get deeper insights from your data.
That's perfectly put. Demystifying the reasoning. That really captures the goal. Okay, so here's a final thought to chew on. Imagine the impact across different fields if we could reliably understand the why behind AI predictions. Think about science, medicine, finance, even just everyday apps where trust matters.
Huge potential.
What other big limitations of today's AI do you think could benefit from this kind of focus on built-in interpretability and transparency? Something to ponder. It's a fascinating direction, and this paper gives us a really compelling look at a more understandable AI future.
Definitely food for thought.
Thanks for joining us for this deep dive on Talk Tensors.